The declassified materials that treat the roar in later years adopt a broader perspective. They attempt to place this persistent mystery within the context of global ocean processes and long-term change. By this time, the existence of a distinct class of deep acoustic events was firmly established. The roar was no longer viewed as an isolated curiosity, but as a recurring feature of the underwater soundscape. One line of interpretation associates the roar with large-scale circulation in the deep ocean. The abyss is not static. Water masses move slowly along pathways that connect polar regions, mid-ocean basins, and boundary currents. These flows carry heat, carbon, and nutrients around the planet. Some modelers suggest that the roar might arise when particular configurations of density, temperature, and topography focus energy into resonant structures. Under this view, the roar would be a kind of natural organ pipe effect on a colossal scale, the manifestation of changing pressure fields in complex geometry. Yet this idea alone does not quite explain the organized internal patterns of the sound. Even when treated purely as fluid dynamics, the hierarchical modulation present in the recordings resists simple characterization as random turbulence. Others therefore propose that the roar may involve interactions between physical processes and biological systems. For example, large layers of gas-rich fluids might be periodically released, expanding rapidly and generating broad-band sound while interacting with dense aggregations of organisms. The organisms, in turn, might react to the disturbance, adding their own contributions to the spectrum. The persistent mismatch between the roar and all known whale calls remains a central point. Marine mammals are masters of acoustic signaling, but their repertoire and physiology have boundaries. Extensive surveys of whale vocalizations, even when including rare and newly documented types, still fail to show convincing overlaps with the roar. Its deepest components reach into frequency ranges that would require resonant cavities of extraordinary size if produced by a single organism. Its overall energy appears several times greater than the loudest whale songs ever measured. Some researchers have raised the possibility of unknown large life forms inhabiting the deepest basins. The argument cites the vast unexplored volume of the ocean and the sparse coverage of observation. Evolution in the deep is slow and often hidden, and there may exist organisms that have escaped detection due to low interaction with human activity. Under this hypothesis, the roar would represent the vocalization or mechanical activity of a biological entity larger and more powerful than any currently documented marine animal. The idea is difficult to test, yet it remains in circulation because no alternative explanation has fully prevailed. From a practical standpoint, the roar carries implications for navigation, communication, and environmental assessment. Its power can interfere with long-distance acoustic systems used to measure ocean temperatures and to monitor for natural hazards. In regions where roar events occur, background noise models must be adjusted. There is also concern that whatever process produces the roar may respond to changes in climate and human activity. As the ocean warms and circulation patterns shift, the frequency, intensity, or distribution of these deep signals might change. The final sections of the declassified files emphasize humility before the unknown. The roar stands as a reminder that even with global sensor networks and advanced modeling, significant aspects of Earth remain mysterious. The deep ocean in particular holds vast unsurveyed expanses where unique phenomena can persist for centuries unnoticed. The roar is one of the rare cases where such a phenomenon has come within the range of our instruments, yet it still resists clear identification. It is noted explicitly in those closing pages that the roar cannot be comfortably assigned to the familiar category of whale sounds. Its acoustic fingerprint differs in scale, structure, and context. It rises from depths beyond the habitual domain of whales. Whether it originates from intricate fluid structures, from interactions among hidden ecosystems, or from an unknown living source of immense size, it speaks in a voice unlike any other recorded in the sea. In that sense, the roar has become less a single mystery to be solved and more a symbol of the continuing frontier beneath the waves. It reminds observers that each apparent certainty about the ocean rests on a narrow foundation of data. Beyond that foundation lies a vast, dark volume where pressure is enormous, temperature is constant, and sunlight never reaches. From that realm, on rare occasions, comes a sound that rolls through the water with an almost living force. Instruments record it, spectrograms display it, analyses dissect it, and yet its essence remains elusive. It is a roar from the deep that is not a whale, and for now it keeps its secret. For many years, the deepest parts of the world ocean were monitored by scattered networks of underwater microphones. These hydroacoustic arrays were originally intended for routine tracking of seismic activity, iceberg calving, and the movement of large marine mammals. Most of the recorded sounds fell into well-understood categories. The lonely calls of migrating whales, the slow rumble of distant earthquakes, and the crackling of shifting ice sheets formed a familiar background. Within that predictable chorus, unusual events appeared from time to time, but they were generally brief and easily explained. The event that would later be labeled only as the roar came without warning during an otherwise ordinary monitoring cycle. A broadband disturbance rose out of the ambient noise floor and expanded into a sustained, rising sound that overwhelmed nearby channels. The signal arrived almost simultaneously at multiple listening stations separated by thousands of kilometers. At first glance, analysts assumed a technical malfunction. This was the usual explanation when recordings appeared saturated or distorted. Yet when technicians checked the instruments and calibration logs, they found nothing abnormal. Every sensor had functioned within expected ranges. Once the initial confusion passed, archived data from each station was carefully synchronized. It quickly became clear that the arrays had captured a real acoustic event that had propagated through vast columns of water. The sound lasted nearly 1 full minute, far longer than most impulsive noises. Its energy spanned a strikingly wide frequency range. The low-frequency component pulsed through the record with a physical presence that listeners later described in technical notes as almost tactile. Superimposed on this deep component were complex harmonics that rose and fell in layered patterns. To understand the event, analysts compared it to an extensive library of whale calls. Modern marine acoustics holds detailed catalogs of vocalizations from blue whales, fin whales, humpbacks, and many other species. Each type of call displays recognizable frequency structures, durations, and repetition patterns associated with feeding, migration, or communication. The roar did not match any entry in those archives. Its pattern was wrong, and its scale exceeded even the most powerful known biological sounds produced by whales. Location estimates were made using arrival times at different sensors. The calculations indicated an origin deep within a remote abyssal plain, far from major shipping lanes. The depth implied by sound propagation models placed the source near the ocean floor, in regions where light never penetrates and where pressure reaches crushing values. No known whales spend extended time at such depths, and no human-made equipment was scheduled to operate there. At first, the official summary framed the roar as an anomalous geophysical event. There were precedents for unusual sounds produced by submarine landslides, volcanic eruptions, and sudden gas releases from the sea floor. However, further analysis revealed inconsistencies with that interpretation. Geological events usually produce distinctive sharp onsets and decays, often accompanied by recognizable seismic signatures. In contrast, the roar built steadily and maintained a remarkably stable structure over its full duration. The most unsettling detail emerged from a fine-scale spectral analysis. Within the broader energy envelope, the sound contained repeating substructures that resembled organized phrases. These structures recurred at non-random intervals, suggesting some underlying modulation process. That discovery shifted the perspective from simple physical event to something more complex, possibly adaptive or even responsive. The initial report, now unclassified, concludes with a cautious statement. The sound was not a known whale call, not a familiar geophysical process, and not an obvious artifact. It appeared to originate at extreme depth and carried an acoustic power that challenged existing models of natural underwater sound production. Subsequent memoranda recommended increased monitoring of the region and careful cross-checking with other oceanographic records. The roar became a reference point in discussions of unexplained ocean noise. It entered technical lectures, internal briefings, and specialized conferences. Yet it remained, at this early stage, a single event, a unique recording that could still be dismissed as an oddity. Only later, with the accumulation of further data, would it become the centerpiece of an ongoing mystery in deep ocean science. After the first recording of the roar, monitoring facilities quietly adjusted their protocols. Data from hydrophone arrays near the suspected source region began to receive higher priority. Algorithms were updated to trigger alerts whenever energy spikes appeared in similar frequency bands. What had been treated as a curiosity now became a specific target for focused observation. Months passed with no comparable events. The noise of the deep returned to its usual mix of whale songs, storm-driven waves, and distant quakes. Some analysts began to suspect that the roar had been a rare confluence of multiple natural sources rather than a single phenomenon. Then, nearly a year after the original event, another recording arrived. This second signal did not match the first exactly, but it shared the same overall structure, a rising low-frequency bed layered with complex shifting harmonics. This time, the arrays captured more detail. Advances in processing allowed for improved separation of overlapping frequencies and more precise timing measurements. When the new event was compared to the original recording, a pattern emerged. Certain spectral shapes returned with small variations, like related motifs in music. The durations of specific segments fell into consistent ratios, implying an underlying rule set rather than random variability. Localization again pointed to the deep basin of the same oceanic sector, but not to the exact coordinates of the first event. The source region appeared to move along a rough arc that traced the edge of a vast underwater plateau. Depth estimates placed it near seafloor features marked in older bathymetric charts, but poorly explored in detail. These structures included steep escarpments and sediment-filled troughs, geological formations capable of affecting sound propagation in complex ways. Efforts to attribute the roar to geology intensified. Undersea landslides can produce long, drawn-out rumbling sounds. Gas chimneys venting from the seafloor can generate continuous vibrations through columns of rising bubbles. Yet when scientists examined seismic records corresponding to the times of the roar events, they found no convincing matches. Seismometers located on distant continents and on sparse ocean bottom stations showed no signatures that would be expected from large structural movements. Attention returned to biology, but not without skepticism. The power of the roar, estimated from its propagation distance and intensity, exceeded the known output of whales by a significant margin. The frequency content extended below and above the principal ranges used by baleen whales. Furthermore, the depth of the source remained difficult to reconcile with whale physiology, which is adapted to a different stratum of the water column. Even the most extreme diving mammals do not linger near the abyssal plains. As more events accumulated over subsequent years, analysts compiled a catalog of roar-type signals. A few occurred within the same basin. Others appeared at great distance, in separate oceans, yet displayed strikingly similar characteristics. Each new entry refined the statistical understanding of the phenomenon. Patterns in timing suggested seasonal fluctuations, possibly linked to large-scale shifts in deep current systems. Some events clustered in particular years associated with strong global climate anomalies. The spectral structure of the roar type sounds attracted particular attention. Advanced computational methods revealed hierarchical organization, with larger segments composed of repeating subunits and microstructures. This organization looked less like simple resonance and more like modulation, with certain frequency bands rising while others fell, in coordinated sequences that repeated with variation. Within the declassified portions of the records, there is a notable shift in language over time. Early reports consistently refer to the roar as an acoustic anomaly or ambiguous event. Later documents adopt more neutral phrasing and speak of an unidentified source process in the deep ocean. The cautious tone reflects a tension between the desire to propose explanations and the recognition that available evidence does not decisively support any single hypothesis. By the end of this period, the roar had evolved from a singular curiosity into a recognized category of deep ocean sound. It was still not attributed to any specific cause, but it was no longer dismissed as mere noise. It represented something persistent, organized, and widespread, echoing through the abyssal darkness with a voice that did not belong to known whales. As the catalog of roar events expanded, attention turned to direct investigation of the source regions. This required specialized technology capable of operating in extreme depths for extended periods. Autonomous underwater instruments were deployed to sit quietly on the seafloor and listen. Mobile platforms were programmed to patrol along isobaths where sound propagation paths suggested likely origins. The deep ocean is a harsh environment for electronics and mechanical systems. High pressure, low temperature, and corrosive chemistry place constant stress on equipment. Many early deployments failed. Batteries degraded more quickly than expected. Connectors leaked. Instruments were sometimes lost entirely, their last transmissions fading into static before contact was cut. These setbacks slowed progress, but they also contributed to the gradual refinement of engineering for the abyss. Over time, the monitoring network improved. Fixed installations recorded months of continuous audio, paired with measurements of temperature, salinity, and current velocity. When roar-type events occurred, analysts could now correlate the sound with simultaneous environmental data. They noticed subtle changes in water density layers near the source regions, as if something displaced large volumes of water or altered mixing patterns in the deep. Efforts to capture unmistakable local recordings of the roar met with mixed results. The sound was detected clearly on long-range arrays, but near seafloor instruments often registered only muffled pulses or strangely quiet intervals. On several occasions, a deep station located close to the projected origin reported nothing at all, while more distant sensors captured strong signals. This suggested a complex interaction between the source and the surrounding environment. It seemed that the sound sometimes propagated up and outward while leaving a relative acoustic shadow close to its origin. In parallel with field deployments, numerical models attempted to simulate candidate mechanisms. Geophysical models explored scenarios involving sudden releases of pressurized fluids, shifting fault blocks, and resonance within underwater canyons. Biological models considered possibilities such as vast aggregations of smaller organisms producing synchronized vibrations, or unknown large animals expelling powerful bursts of air or fluid through specialized cavities. None of these models fully replicated the observed spectral patterns and propagation behavior. Chemical analyses of deep water samples from roar-associated regions found faint anomalies. Concentrations of dissolved gases showed slight deviations from background levels, with occasional traces of methane and other reduced compounds above expected values. However, these signals were not strong enough to support decisive conclusions. The deep ocean is a dynamic chemical environment, and many processes can produce such variations. One intriguing observation involved the behavior of other sounds during roar events. Recordings showed that ambient noise decreased sharply in certain bands just before and during the main pulse. Biological activity, such as the clicks and calls of smaller organisms, appeared to diminish temporarily. It was as if the surrounding soundscape retreated or was suppressed. The water itself, in acoustic terms, grew quiet around the growing roar from the deep. This quieting effect fueled speculation about pressure fields and energy absorption. Perhaps the source process did more than simply emit sound. It might also organize the medium around it, altering the way other vibrations travel. Such a process could be mechanical, related to large-scale water movement, or it could involve more subtle interactions between temperature, chemistry, and acoustic properties. The declassified analyses portray an ongoing struggle to reconcile these observational threads. The roar is powerful, yet often associated with areas of local silence. It appears in multiple oceans yet maintains a consistent structure. It coincides with slight changes in deep water conditions, but does not fit neatly into known cycles of currents or climate indexes. Simulation after simulation falls short of capturing all aspects at once. By the end of this phase of investigation, reports began to describe the roar not only as a loud signal, but as a phenomenon that rearranges the acoustic character of its surroundings. It was not just another sound in the ocean. It was an event that seemed to reshape how the ocean itself transmitted sound, at least for a brief period, before fading back into the normal background of the abyss. We upload new videos every single day, so make sure to subscribe and turn on the notification bell so you never miss what's next. If you enjoyed this video, don't forget to leave a like, it really helps the channel grow. Tell us in the comments what you'd like to see next. Your ideas might be in our next upload. Thank you so much for watching and for being part of our community. Stay tuned, stay curious, and we'll see you in the next video.